Hello and welcome. Find a comfortable position. Allow your body to settle. Tonight we are not traveling toward the light of a distant star, but toward a profound and chilling absence. We are journeying to a place in the cosmos that shouldn't exist. A vast patch of sky, billions of light years away, that is unnaturally cold. What if the greatest secret of the universe is not hidden in the heart of a brilliant galaxy, but in the depths of an immense and silent void? Join me as we explore the mystery of the cosmic cold spot, an anomaly that could be nothing, or it could be everything. To understand the cold, we must first understand the warmth. Imagine the entire universe just after its birth. It was a hot, dense, brilliant fog of energy and light. As space expanded over billions of years, this primordial light stretched and cooled. Today, it bathes the entire cosmos in a faint, invisible glow of microwave radiation. We call it the cosmic microwave background, or the CMB. Think of it as the universe's first baby picture, a gentle warmth left over from creation. And for decades, our scientific models predicted that this warmth should be almost perfectly uniform, the same temperature everywhere we look. And it is, with one baffling exception. Our story begins in 2004 with a satellite named BUMAP, the Wilkinson Microwave Anisotropy Probe. Its mission was simple: to create the most detailed map ever of that ancient light, the cosmic microwave background. As the data poured in, scientists saw exactly what they expected: a beautiful, almost uniform tapestry of warmth. But as they looked closer, in the direction of the constellation Eridanus, they found something deeply unsettling. A patch of the sky was significantly colder than the rest. It was not a small blip. It was a colossal anomaly spanning 1 billion light years across. To comprehend the scale of this void is to touch the edge of imagination. 1 billion light years. If you could travel at the speed of light, it would take you 1 billion years to cross from one side to the other. Our own Milky Way galaxy is a mere 100,000 light years wide. You could fit 10,000 Milky Ways side by side into this chasm of cold. It is a structure so vast, so empty, that its very existence challenges our understanding of how the universe is built. Let us visualize what this emptiness means. The universe is not a random scattering of galaxies. It has a structure, a magnificent cosmic web of filaments and clusters, like a great, glowing neural network. Galaxies are strung along these filaments, with vast, dark voids in between. This cold spot seems to be located in the direction of one such void, but one that is impossibly large and unusually empty. It is a region where there are thousands upon thousands fewer galaxies than there should be. A place where the great cosmic song of creation fades into an unnerving silence. The first and most logical explanation put forward was that of a supervoid. Scientists theorize that this patch of sky is cold because there is simply less stuff there. It is a colossal, underdense region of space, perhaps the largest single structure ever discovered by humanity. They named this hypothetical chasm the Eridanus Supervoid. The theory was elegant and fit within our known laws of physics. It proposed that the coldness was not a feature of the ancient light itself, but an illusion created by the void it had to travel through, to reach us. Imagine a photon of light, a tiny particle from the cosmic microwave background, beginning its 13.8 billion year journey towards Earth. As it travels through the universe, it passes through regions of higher and lower density. When it enters a supercluster of galaxies, the gravity of that cluster gives it a tiny boost of energy. When it leaves, that same gravity pulls on it, taking the energy back. Usually, this process balances out. The photon arrives with the same energy it started with. But something strange happens when a photon crosses a supervoid. This is explained by a phenomenon known as the integrated Sachs-Wolf effect. As the photon enters the void, it loses a little energy climbing out of the gravitational well of the matter surrounding the void. It then travels through the vast emptiness. But while it is inside, the universe continues to expand, driven by dark energy. This expansion stretches the void, making it shallower. So when the photon leaves the void, the gravitational hill it has to climb is smaller than the one it descended. It doesn't regain all the energy it lost. It emerges slightly weaker, slightly colder. And over 1 billion light years, that slight cooling adds up. Let us take a moment to drift through this proposed supervoid. Close your eyes and imagine leaving our own vibrant, crowded Milky Way behind. The familiar constellations fade. The dense rivers of stars thin out. We journey for millions of years, then hundreds of millions. The universe around us becomes sparse. The great cities of light, the galaxies, are few and far between. Here in the Eridanus Supervoid, the silence is absolute. There is more space between things than there are things. We are floating in a cosmic desert, a region where the fabric of space-time itself seems emptier, quieter, and colder. But here, the simple explanation begins to crumble. As astronomers peered deeper into the void with powerful telescopes, they began to count the galaxies within it. Yes, the region was underdense. There were certainly fewer galaxies than average, but according to their calculations, it was not nearly empty enough. The supervoid, as observed, could only account for a fraction of the coldness seen in the CMB. The effect was real, but it was too weak. The void was there, but it wasn't super enough. The mystery, far from being solved, had only deepened. The search for these missing galaxies is a painstaking task. It is like trying to count faint, distant candles from across an entire ocean. Astronomers use deep sky surveys, mapping the three-dimensional positions of hundreds of thousands of galaxies to build a true picture of the cosmic web. And every survey that has looked in the direction of the cold spot has come to a similar conclusion. The void is real, but it cannot, by itself, explain the profound chill we observe in the universe's oldest light. Something else must be at play. Think again of the cosmic web, this filigree of light and matter stretching across the eons. It is a structure born from the tiniest quantum fluctuations at the dawn of time, amplified by gravity over billions of years. Matter pulled together to form the filaments, the great walls of galaxies. The spaces left behind became the voids. This is the natural, expected architecture of our universe. The cosmic web is strong, resilient, and its patterns are predictable. The Eridanus Supervoid, however, feels like a deviation from this pattern. If the cosmic web is a delicate, intricate fabric, this void is like a great, gaping hole. It is a tear in the otherwise consistent structure of the cosmos. It whispers to us that perhaps the initial conditions of the universe were not as perfectly smooth as we believed. It suggests that, on the grandest of scales, there are anomalies, strange pockets of existence that do not quite follow the rules. As we contemplate this echo of nothingness, we must ask what it means. In a universe teeming with energy, with exploding stars and colliding galaxies, what is the significance of a place defined by its absence? Perhaps it is a reminder of the universe's default state: cold, dark, and empty. The light and warmth we see in the stars are the exception, not the rule. This void is a glimpse into the profound silence that underpins all of existence, a silence we can listen to as we drift off to sleep. With the supervoid theory proving insufficient, scientists had to turn to more exotic, more mind-bending possibilities. What if the cold spot is not an absence of something, but the presence of something truly strange? What if it is a scar on the fabric of our reality? This leads us to the second major theory, that the cold spot is a cosmic bruise left behind by a collision with another universe. This idea stems from a branch of theoretical physics known as string theory, which predicts the existence of a multiverse. In this view, our universe is not unique. It is just one bubble floating in a vast cosmic ocean, a higher dimensional space called the bulk. And in this ocean, there are countless other bubble universes, each with potentially different laws of physics, different histories, different realities. And sometimes these bubbles might collide. Imagine, in the very first moments of time, our infant universe was not alone. As it rapidly expanded, it gently bumped into another bubble universe. The collision would not have been destructive, but more like two soap bubbles touching and pressing against each other for a moment before drifting apart. This brief, ancient encounter would have sent a shock wave of energy rippling through our own cosmos. It would have literally pushed energy and matter out of the contact point, leaving behind a lasting imprint. This cosmic bruise would have created a vast region of slightly lower density in our early universe. This region would then evolve into a supervoid, but its origin would be far more extraordinary than a simple, random fluctuation. The ancient light from that direction, the CMB, would appear colder, not just because of the void it passes through now, but because it was intrinsically colder from the very beginning. The cold spot would be a fossil, a remnant of an interaction with a universe beyond our own. The energy signature of such a collision is fascinating to consider. The interaction would have a specific texture, a certain pattern around its edges that physicists are now trying to model. They are searching the detailed maps of the CMB for these subtle signs, these ripples that might prove the spot is more than just a void. If they were to find such a signature, it would be the first ever observational evidence that we are part of a much larger, grander multiverse. The philosophical implications are staggering. If the cold spot is a cosmic bruise, it means we can see the edge of our universe, not in space, but in cause. It would mean that the entirety of our known existence, every star, every galaxy, every one of us, has been shaped by an event that originated outside of our reality. It would transform our place in the cosmos from being the center of everything to being one small part of an infinite, interconnected cosmic foam. Of course, this is where science fiction and science fact begin to blur. The multiverse hypothesis is incredibly compelling, but it has a significant problem. It is, for now, almost impossible to prove or disprove. We cannot visit another universe to confirm its existence. We can only look for these faint, indirect shadows it may have cast upon our own. The cosmic bruise theory remains a tantalizing but speculative idea, a beautiful piece of mathematics waiting for definitive proof. This leaves us with a third possibility, one that is perhaps the most humbling of all. What if the cold spot is neither a void nor a bruise? What if it is a sign that our fundamental understanding of the universe, our standard model of cosmology, is incomplete or even wrong? What if the cold spot is a crack in the very foundations of our knowledge, pointing the way to a new, undiscovered physics? The standard model of cosmology has been incredibly successful. It explains the Big Bang, the expansion of the universe, the formation of galaxies, and the nature of the cosmic microwave background. But it is built on a few key assumptions, such as the idea that the universe is isotropic and homogeneous, meaning it looks the same in all directions and in all places on a large enough scale. The cold spot, along with a few other large-scale anomalies, directly challenges that assumption. Perhaps the laws governing dark energy, the mysterious force accelerating the expansion of our universe, are not as simple as we think. Perhaps this force interacts with the fabric of space-time in strange ways, creating vast pockets of cold that our current theories cannot predict. The void could be a place where dark energy behaves differently, pushing matter away more aggressively and cooling photons more effectively than we ever imagined. The cold spot could be a window into physics beyond our comprehension. In science, anomalies are often the most exciting discoveries. They are the loose threads that, when pulled, can unravel an old paradigm and reveal a new, more accurate picture of reality. This unnaturally cold patch of sky might be the most important clue we have in our quest to understand the 95% of the universe, dark matter and dark energy, that remains completely mysterious to us. Let us pause now and simply listen. Listen to the sound of this cosmic silence. The temperature of the cosmic microwave background is about 2.7 Kelvin, just a few degrees above absolute zero. The cold spot is only 70 microkelvin colder than average, a tiny fraction of a degree. And yet this minuscule difference, stretched over 1 billion light years, whispers of other universes, of new physics, of the profound and beautiful emptiness that forms the canvas of our cosmos. It is a silence that invites calm, a cold that brings peace. Years after WMAP, the European Space Agency launched the Planck satellite. It was a far more powerful and sensitive instrument designed to map the CMB with unprecedented precision. scientists around the world held their breath. Would Planck reveal the cold spot to be a mere statistical fluke, an error in the older data, or would it confirm its existence? The results were unambiguous. Planck saw the cold spot even more clearly. The anomaly was real. It was not an illusion. It was a true feature of our universe, demanding an explanation. This leaves open the simplest and perhaps most unsatisfying explanation. It could all be a coincidence. In any random dataset, no matter how large, you will find strange patterns and outliers. It is possible, though statistically unlikely, that the cold spot is just a 1 in a billion random fluctuation in the primordial plasma of the early universe. It may have no special cause at all. It might just be the universe dealing a strange hand, a cosmic cold flush. This idea touches upon a deep philosophical concept in cosmology known as the Copernican principle. It is the idea that we and our location in the universe are not special. Earth is not the center of the solar system, and our galaxy is not the center of the universe. But if the universe has these strange, unique anomalies like the cold spot, does that make our observable universe special? Does it violate this principle? Or are these features common and we just happen to live near one? The cold spot does not exist in isolation. As we have studied the CMB in greater detail, other strange, large-scale alignments have appeared in the data. There is a mysterious alignment of patterns in the CMB with our own solar system, nicknamed the axis of evil, which also shouldn't exist if the universe is truly random. These anomalies, taken together, suggest that the cosmos on its largest scales may be stranger and more interconnected than our theories allow for. The future of this mystery lies with even more powerful instruments. Telescopes like the Euclid mission or the James Webb Space Telescope are designed to map the distribution of galaxies and dark matter with incredible accuracy. They will peer into the heart of the Eridanus Supervoid and give us a definitive census of what is there and what is not. They may finally tell us if the void is empty enough to explain the cold, or if we must embrace a more exotic explanation. And so, our journey through the great cosmic void comes to an end. We pull our consciousness back across the billions of light years, past the distant galaxies and nebulae. We return to our own spiral arm of the Milky Way, to our familiar sun, and back to this small blue planet. We return to the comfort and safety of this room, to the gentle weight of your body as it rests. The great cold void remains out there, a silent question mark written across the sky. Tonight, we have stood at the edge of one of the universe's greatest mysteries. We have considered the possibility of a colossal supervoid, a region of profound emptiness that chills the very light of creation. We have dared to imagine a cosmic bruise, the faint, lingering touch of a parallel universe against our own. And we have faced the humbling idea that our most cherished theories of the cosmos may be incomplete. The truth of the cold spot remains elusive, a puzzle for the next generation of dreamers and explorers to solve. But its existence reminds us that the universe is not just what we know, but a vast and beautiful ocean of the unknown. It is a place of infinite wonder, perfectly suited for a night of deep and peaceful dreams. Thank you for joining me on this journey. If you enjoyed this lecture, please consider subscribing for more cosmic explorations. Like the video to help others find a moment of peace. And I invite you to share in the comments below which theory about the cold spot do you find most compelling? The simple void, the cosmic bruise, or something else entirely? For now, let the silence of the cosmos be your guide. Let the mystery lull you into a deep and restorative sleep. Good night.